Hi, everybody, and thanks a lot for inviting me over. And for coming. Of course, it's been way too long since my last visit. It was very exciting so far to see all the very cool work going on here. Today, I want to tell you, of some recent work we've done, especially using depth cameras for certain reasoning problems in robotics. And ultimately, what we would like to achieve is, of course, robots that can reason really about what is going on around them in the environment, right? What are the people doing? How can it solve certain tasks and things like that? So ultimately, where we would like to go is something like this. And this is a mock-up, so this is not our robot really doing these kind of things. But we'd like to have robots that can interact with people in a natural way, that can then solve complex tasks and even learn how to solve tasks from people around them. This is an example setup where imagine having a robot in a wet lab where you do experimentation, right? It's kind of what we call a structured task environment. You could also imagine cooking at home where you have certain complex tasks that you want to solve. And I think it would be nice if we could just interact with the robot this way, where we just show it something and say, hey, this is one of the test tubes. And the robot then recognizes in the future what these test tubes look like. And then we have to tell it, okay, now pick one up and let me show you how to shake it. Because, for example, it turns out it's important, like how they shake them in these experiments and things like that. So you should be able to tell the robot how to do things. And ultimately, then you just say, okay, now let's solve some more complex tasks together, right? Where some steps are being done by the robot and other steps are being done by the person. And ultimately, of course, if you want to do this requires a lot of understanding on the robot side. So on the one hand side, of course, there's the speech and natural language processing side, understanding what the person is saying. I'm not going to talk about that today at all. We've done some work on semantic language processing, language understanding, that I point you here at some papers if you want to look at those, but I'm not going to talk about those. At the same time, the robot needs to be able to recognize objects in the environment. It needs to be able to also kind of track them and how the person and the objects move through the space. And it has an understanding kind of the activities that are going on. Just to step back in time a little bit, about 7 years ago, the main sensor that we used in robotics, that virtually every group was using, is a SICK 2D laser scanner that you see here, this blue box on the robot. And I'm sure when you're working with Joydeep, you've seen a lot of this kind of data. And what you could do with these kind of sensors is build nice 2D maps of an environment. You can see this here on the left. I'll show you a brief run of a robot kind of exploring. Part of this is of the Allen Center, where you can nicely stitch the sensor data from the laser scanner together, and white space is free space and black are obstacles. These are what we call an occupancy grid map. And the sensors are very well suited for building these kind of 2D maps. Here's a problem that we call loop closure, where the robot has to recognize that it went back to where it kind of had been before, and then it can use this to align its data to build a consistent map. You can see this going on again when the map kind of shifts into place. At that point, also kind of the pure navigation in these kind of environments was not fully solved, but I think especially also with the work that Joydeep has shown, that with these kind of sensors, we can now really navigate very robustly in these kind of environments over 1,000 miles or huge distances, 1,000 kilometers. The problem is, of course, that this kind of sensor data is really not sufficient if you want to solve this kind of interactive robotics problems where it's about reasoning what the people are doing around you. The other kinds of sensors that we were looking at, of course, on the right side, you see what came up at that time is a 3D laser scanner Velodyne, which is the main sensor that, for example, the Google driving cars are based on. So hugely expensive and mostly for outdoor robotics. If you wanted to do human-robot interaction kind of task where you wanted to track the people, then typically what you had to do is put a person in a motion capture lab and into one of these funny motion capture suits. Finally, of course, there were cameras out there, but at the time, people didn't really know that well how to use them also, because the kind of data that you get from these cameras is not that well suited, for example, for telling you where certain objects are in the world. And what people were able to do was just not robust enough for robotics. So at that point in time, is when the Microsoft Kinect system came out, what we call these RGBD depth cameras. And the main purpose of this sensor in the Kinect system was actually to track people in gaming environments. And here I'll show you just briefly what the data looks like, the raw input data that we get from such a depth camera. And at the time I was lucky enough that I was directing an Intel research lab in Seattle, and as an Intel person, we were able to get our hands onto early prototypes of that camera. So we were really excited when we were able to see this kind of data. So what you see here is on the left, kind of the standard color video sequence that you see. And on the right, we get from the camera, at 30 frames a second, we're getting kind of distance estimates for how far in the world every pixel is away from the camera, where red is close and blue is further away. And you can see it's not perfect because these black areas are areas where the camera doesn't give you depth information. So for example, glass, very shiny surfaces or things like that are not visible. But still, this kind of information is so much richer than, for example, just raw color data. And especially for robotics, this was really, really exciting because for a robot, what you care about is how far things are away. Right? On the one hand side, if you want to avoid crashing into something, it's good to know where the obstacles are. Or if you want to pick something up, it's also very useful if you know where that is in the 3D space. So that is why these cameras really had, since then, a tremendous impact on robotics. One other thing now moving forward that we would like to be able to do with these kind of cameras is something that I might call like the 100-100 tracking challenge. So this is a person doing an experiment in a wet lab. And it's observed by 3 different depth cameras at 3 different locations. It's time synced. On the left, you see the color, and on the right, you see the depth information. Again, you can see it's not perfect. But I think ultimately what we should be able to do is, if I tell you, install that system in a wet lab, for example, which means you know what kind of environment it is. You might be able to build a 3D model of the environment. You might be able what kind of objects the people are interacting with, like test tubes and things like that. I think what we at some point might be able to do is to label more or less every single pixel in that data stream and tell you what that pixel corresponds to. So for example, are the objects in the scene? This is the 6D pose of an object. This is how it's moving through the scene. And also to identify the motion of the person. And then also feed this up into higher level recognition systems so that you can reason about the activity that's actually going on. So ultimately, I think we need to go beyond what's a lot of focus also in the vision community, let's say bounding box kind of tracking. I think it's not enough to be able to just say there's a hand somewhere here in the image, but we would like to know actually the pose of the hand so that we can learn by how the human interacts with objects. Or it's also not sufficient to have an activity label that says the person is pipetting right now. We would like, or from a robotics perspective also, we would like to know how is the person holding the pipette in the hand and how is the person moving and things like that. Okay, so this would be the ultimate goal, I think. If we could do this, then that would be extremely useful, of course, for robots because they would have a really deep understanding of what's going on around them. So what I want to show you today is kind of give an overview of some work we've done using these depth cameras for certain tasks. And related to this kind of understanding of the environment, there are different kind of sub-problems that I choose here kind of to order things by. So the first one is about modeling, building 3D models of the environment, 3D models of objects and people. Then once you have models, for example, you would like to track them through time, how things move through time, and especially what we call articulated scenes, which means things that are somehow connected through joints, like the human body very much. Then tracking only works if you have an initial pose estimate for the objects you are tracking. So the next problem we have to look at is detecting these articulated objects. Right, like if they come into the scene, what is the pose of the object? And finally, some very recent work that I just want to show, because I'm excited about it, is about talking about liquids, which is something that is just not so easy to model anymore. And some recent work we started doing in this domain. And then, of course, I'll come to discussion. But let me start with modeling, 3D modeling scenes. And that was kind of the first thing we started when we got our hands onto these depth cameras, was trying to build a 3D map, because in robotics, of course, building maps of environments is one of the the big problems we all want to solve. So we said, having these cameras available now, we can build finally real 3D models rather than, let's say, 2D occupancy grid maps. Okay, and this is work that Peter Henry started, and the underlying techniques were kind of very much based on standard approaches that people used in computer vision and in robotics, using matching techniques between data frames. And the subproblems that you have to solve if you want to build a consistent map of an environment are these 3 problems that you also had already seen when I showed you the 2D mapping with the laser scanner. Okay, where the first part is what we call frame-to-frame alignment, or some people might call it visual odometry, where let's say you walk with the camera through an environment, or the robot moves with the camera through an environment. In order to stitch the data together into one consistent map, what you have to do is between 2 consecutive camera frames, you have to know the motion of the camera. Okay, how did it move through the 3D space, or it's a 6D with rotations. Okay, and what you do is you just take the 3D scan of the previous frame and then match it against the next frame. And I'll show you some examples for that later in other contexts. But it's kind of matching the frames together so that they fit in the 3D space. And you can also do this using color features in order to improve this matching. What that gives you is now kind of a forward motion estimate for the camera. So again, that's what's also called visual odometry. Now the problem is when you walk around a big loop of a hallway and then you come back, over time you're going to accumulate drift in these estimates. So the estimates are not perfect, so you're going to get some inaccuracies, which means as you come back to a location where you've been, your map doesn't really match exactly. The pose is kind of different, it's off. Okay? So what you have to do is first you have to detect that, oh, I've been here before, and you have to match it against that previous observation. And for that we just used the visual data and did some very standard kind of SIFT-based feature matching between the current image and the images that we've seen in the past. And once you observe that loop closure, you just kind of use that additional information to refine all the position estimates that you have done so far, which is you just do what's called a global alignment, which means you globally optimize over all the camera poses in the past to come up with a consistent map. Let me just show you one example for how this works. This is now the step where we're just doing, let's say, visual odometry forwards, which means we're stitching all that data together. At some point, you're going to see here, we can detect a loop closure because it's visually the same. And then we can use this, you can see this now, to snap things into place. Very similar to the 2D laser scanning that I showed you, but now the whole thing just done in 3D. Okay. Another project we did then was also we worked with Nick Roy at MIT, who is doing work with quadcopters. So we put it on a quadcopter, and then now you can build kind of full 3D maps on a quadcopter. Okay, and there are nowadays many different techniques for building these kind of 3D maps with depth cameras. So that's why I'm not going to go to any real depth here, but just to give you some examples of what we can do. Okay, and at that point, the representation of the map is either typically we use, it's kind of a 3D colored point cloud, okay, where these depth maps give you points in 3D space, and we use the color that we get from the color camera at the same time. Or we also represented these surface elements by so-called what's called surfels, which are little disks in space that represent surfaces. Okay, and then Richard Newcomb, he worked at an internship at Microsoft Research in Cambridge in the UK, where he developed this technique called Kinectfusion that I'm sure many of the students have seen and heard of, and that was really also an eye-opener because they showed how you can build in real time very high accurate maps of at least local areas. Okay, I'll just show you a brief video here on the right soon, but the main idea is that you have a 3D volumetric representation of the space, and in each of these voxel grids, let's say a voxel is just, let's say, 1 by 1 by 1 centimeters big, so pretty fine-grained, and in the voxels you do not store whether it's occupied or not, which would be the natural thing that people had done before, but you actually store something that is called a signed distance function. And what you store in the signed distance function is, let's say if I'm getting a certain depth estimate along a pixel ray in the camera, then what I'm storing is along that ray in the pixels, I'm storing how far in front or behind my measurement they were. Okay, so at the measurement, I'm going to store a 0 distance, and in front of them, I'm storing -1, -2, -3, -4, and behind this, I store like increasing positive values. I'm doing this what's called a truncated sign distance function, which means I'm only doing this close to the surface. And it turns out that this representation is extremely well suited to first incorporate information over time, incorporating multiple of these depth maps, which is something that Brian Curlis already did as part of his PhD thesis, coming more from the graphics community. But they are also well suited for matching scans against a model, okay? And what you see here is now, in this video here, on the upper left portion, you see kind of the input data. And I think the most interesting part is the one on the lower right, where you'll see the map that is being generated by this. Okay, and again, the main insight here is that we can now build pretty high accurate 3D maps, and this can be done at 30 frames a second, okay, using GPU processing. And again, the 3D voxel representation itself just stores the sign distance values, but it turns out that you can very efficiently extract a mesh, a vertex mesh from that. Okay, and you can render from this. So you can see here on the right, able to see kind of the 3D representation. Here's just another map that now, for example, my student Peter Henry added, for example, to Kinectfusion some notions of using also color for the matching. So it's jointly matching using color information and depth information. And also kind of having an ability to do loop closure in these kind of models. But you can see that nowadays we can actually get pretty good 3D models of these environments. Okay? But you can also see clear limitations. So for example, in the upper left, there's lots of that's not modeled very well. And that is because, for example, these are plastic bottles. And the plastic surface is not detected very well by the camera. Okay? So there's still many limitations that are in there. Another limitation is, for example, if you want to model small objects or a keychain or something like that, it's not clear how we should even represent that. So there's still many open questions in this area, but I think we're at the level of getting pretty good 3D models nowadays. So this is again just built by walking once through this bay in the wet lab. One project we looked at was also how can we enable robots to autonomously build models of objects. So you could imagine the robot moves through the environment or through your house, and there's a new object. So it should be able to pick up the object and build a 3D model of that. Okay. So here you can see kind of our first approach where the robot has the object in the hand, and we are using the depth camera to track the arm of the robot and to jointly build the model of the object. You can see here on the right side how the object model is being built as the robot is moving it in front of the camera. And the approach for this is very similar to the kind of environment modeling that we've done, because whether you build an object model of the environment, it raises the same kind of question. So we also do things like loop closures on the object model now. So what you see here is kind of now a technique that enables a robot to build these 3D models. And on the right side, you see some examples of objects that we can build. One question now is how should the robot actually move the object in its hand in order to build a complete model? Because the motion itself depends on the shape of the object itself as well. Okay, so in this context, we took advantage of the fact that with the sign distance functions, we're not only modeling, let's say, the surface of an object, but we can also get an estimate for how uncertain we are in the surface. Yeah, you can see this on this slide where I'm showing you on the right, kind of as an object model is being generated, I'm showing in the coloring the uncertainty we have in the surface element. And that uncertainty just depends on how often did I look at a certain surface element and from which angle did I look at it. Okay, so red means high uncertainty and silver gray is then when we get lower uncertainty. So as surfaces come new onto the model, there's of course higher uncertainty, but as we see more of those surfaces, the uncertainty decreases. The good thing is now we can use this representation for the robot to determine from where it should look at the object in order to decrease the uncertainty. Okay, it's very simple where, let's say you have this partial object model, you have a notion of the uncertainty that you have, and then we simulate multiple viewpoints and choose a viewpoint such that if I look at the object from here, then I'm going to maximally reduce my uncertainty, measured as entropy over the surface. And then what I'm going to do is if I choose this viewpoint, I'm just going to rotate the object such that the viewpoint corresponds to the camera itself. Yeah? And this is kind of how it then works on the robot. So where the robot picks up the object, and initially, to get kind of an initial idea of the kind of object, we do just a pre-programmed kind of trajectory here. And now it's already starting to build up this 3D model. And at some point, it takes the model it has so far, along with the uncertainty, here. And then it determines how to look at this object so that it reduces the uncertainty as much as it can. And then in this case, it's actually rotating it so that it can look under the stuff there. That's on that face. You can see that now it's starting to reduce uncertainty here. I don't have it in this video, but what the robot also considers its own hand, which means it can reason about occlusion. So for example, if I hold this object here, I will never perfectly see the surface underneath my hand. So the robot can then actually put the object down and compute a new grasp that mostly exposes these uncertain surfaces. So after 2, 3 of these regrasps, it has then a complete model of the object. Okay? So now we are able to build objects of 3D environments, and with this kind of technique, a robot might even be able to autonomously build 3D object models. One more thing that's tricky to model is people. Okay, so this is some recent work that we did with Richard Newcomb when he was a postdoc with Steve Seitz and me. And so again, Richard, he built this Kinectfusion technique, okay, which builds these really nice fine-grained 3D models. The problem is, if you apply Kinectfusion on a person that's kind of moving the head, then the model you're getting is going to look like this. Okay, where it's just averaging over the data, kind of, right? And that's clearly not Richard's nose. Okay, so the problem is that, again, the modeling approach assumes that nothing is moving in the scene, or the only thing that's moving in the scene is the camera. And if the head is moving, then what's going on is more or less the model is just averaging over the surfaces it's seeing. Okay, so that brings up the question is how can we build a 3D model of that person as the person is moving? Okay, let me just show you one example of how this is working. So this is showing Jessica, and there's a laptop, and on the laptop you can see the depth camera up there looking at her. And in the video you will see on the upper right, you see the raw input depth video. And on the lower right, what you will see is the 3D model that we're building in real time projected into the data so that you can see that it's kind of consistent with what we're seeing. Okay? So you can see how the model on the lower right is being completed as she's moving her head into different orientations. Okay? And again, using high-end GPUs, Richard was able to get this to work at 30 frames a second. Okay? I'll give you a bit more insight on how this actually works. All right, so the main idea is the following actually. So again, in Kinectfusion, we have this 3D voxel grid with the sign distance functions that I mentioned. But again, these are kind of static. Okay, so what dynamic fusion does is it represents the scene by 2 different representations. So the one is a static model, which means we're still building a static model of the person. And in addition to that, we're building a 3D volumetric warp field that says how the different points or surfaces in this static 3D model need to be moved such that they match the data that you're seeing right now in real time. Okay? So what you see here is, again, we have as input the depth video. From the depth video, we are asking a so-called volumetric motion field that says how things in the 3D space move. And that helps us to build a 3D static model of the person. And that 3D model is also fed back into the volumetric motion estimation field. And then what we get out of that is kind of a non-rigid reconstruction. Okay? So again, at every time, the key trick is we're taking the current model that we have, we're taking the current motion estimate that we have, we're feeding the model through this motion field, match it against the input data that we see, and then use this matching process to update the motion field and the 3D model. And by doing this over time, and by taking advantage of the fact that if you're doing this at 30 frames a second, the motion between individual frames isn't that large, then we can build this model. So here's just another example of this kind of volumetric motion field where I'm showing you on the left a static model and just one slice of this motion field. Okay, so we have to do this in a full volume. I'm showing you one slice, and on the right you can see what a warped model then looks like. Okay, once we feed it through this motion field. Okay, so we can handle pretty rich motion and pretty fine-grained motion as well. And again, the trick is that we estimate the motion field along with the reconstruction. Let me show you one more example. On the right, you see the reconstruction. And you can see as new parts of the cup get exposed, that the model of the cup gets also updated. Even though it's moving through space, you can see it now here, for example. Okay? So this is what I want to say about the 3D modeling aspects of environments, objects, and people. Any questions about that? Or yeah?
So if you do this at slower frame rates, it's harder.
Yeah, that's a cool thing that also, like Andy Davison's lab, what the insight is, we used to say, okay, let's assume I have an algorithm that works at whatever, 10 frames. And then you would say, oh, but now if I have a camera with 30 frames, it's never going to work. But the idea is that if you have a higher frame rate, then the optimization problem between the frames gets easier because the motion is smaller. So higher frame rate does not necessarily mean it gets harder or something like that. It makes actually the estimation problem easier.
And computation.
Yes. But the computation itself can also get faster because the steps you need in your optimizer is less. Right? Okay. Then the next problem is, so now let's assume we have these models. The next problem is we want to track them as, for example, people are moving in the scene, right? Because we don't want to constantly build new object models. In that case, we did some work on what we call articulated scenes. And the approach was called dense articulated real-time tracking, this work that Tanner did together with Richard. So the idea is that we don't want to only track, let's say, rigid objects like this bottle, okay, but we also want to track things that move themselves. So for example, you can represent like a person is one of these articulated objects where we have rigid parts and they move against each other through joints, okay, transforms on these joints. You can have a robot like the Baxter robot here that can represent that way, or a robot, a human hand. On the right side, even furniture can be represented as articulated objects or as an articulated scene where you have a door that has a certain joint and you can open it through this. Okay? So the goal now is how can we track these objects through time, given that we have an initial pose estimate. Yeah? And the key trick is we're representing the individual parts of the objects through, again, these signed distance functions, which is exactly what Kinectfusion did as well. And with these signed distance functions, we can very efficiently match the objects against the data. Okay, I'll show you a bit more on how that works. So here's just an example of kind of a very simple manipulator, how we represent that as an articulated object. So we have, in this case, it has two joints and two joints. So we represent that as these coordinate frames. And in this case, we have 8 degrees of freedom. First, we have 6 degrees of freedoms for the root node, okay, which means where it is, and then we have these other, and this is now the signed distance function representation of that manipulator. Wait, maybe I should stop that briefly. The nice thing is, if I have this 3D representation of the manipulator, I can very efficiently compute or look up distances from the surface of that manipulator, which is what the signed distance functions give us readily. So which means I can very quickly look up any point in space and say this point is that far away from the object. And I can also very quickly compute the direction in which I should move that point to get it closer to the surface. Yeah? And I can also compute, and these are the isocontours of this distance function of a slice, and I can also, of course, compute these depending on the articulation of the manipulator. Okay? And we can now use these sign distance function to very quickly match our model against depth data that we are observing. Let me just give you one example. This is simulated right now, where let's assume we have a robot. This is a robot hand, and the robot hand holds this object it's holding, and we are observing this object with a depth camera, which you will see as these black points coming up. Here's the depth camera view. Okay, and now let's assume that the model doesn't really fully match the data. Okay, so the black is the observed depth data, and the gray is the model. So what we would like to do in tracking is we want to match our model into the data, and if we do this at every time step, then we track the object. Is that clear? So now what we can do is, because the robot hand and the object are represented with these sign distance functions, we can very quickly, for every point that we observe, these black points, we can compute how far it's away from the hand model. And you can see here in this case, I'm coloring those object points by the distance. This is just a slice through this, where red means far away and blue means close. And now we just do optimization, stepwise optimization, Newton steps, in order to match that object against the data. Okay? Now, and again, we can do this very efficiently. So after this step, we just match the object into the data. But imagine on a robot, you could have some additional information like touch sensors. So in this case, imagine these two fingers, the robot detected that these two fingers are touching the object. Yeah? But because of occlusions, it might not see the finger itself. Right? So what you might get is an estimate like this, where the second finger is not touching the object, but because we're doing this model-based optimization, we can also take this into account and make sure that our optimized position obeys that constraint. So we can optimize it such that the finger is actually on the surface of the object. Yeah? Another constraint here that we are violating in this case, actually these two fingers are kind of sticking into each other, as you can see. Right? And typically, we assume that objects don't just interpenetrate. So we can, again, model that using the sign distance function as a constraint, and we can then take that into account in our optimization, and then make sure that the fingers don't interact. Right? So we can push them apart. Okay? So, and the important part is we're not doing this one after the other, but you can all phrase this as one joint optimization over all of these. And here's an example on where we did this in collaboration with the German Aerospace Society near Munich on a robot, where on the upper left you can see the viewpoint of the robot. Here is where the robot is tracking its own hand and the objects as it's manipulating it. So we can do pretty nice fine-grained control of the manipulator now, so that it can pick up the object, it can hand it over. And again, all of this is done with feedback control using the visual feedback. And in this case, the good thing is if the robot, for example, drops the object, because we're doing this in real time, we can track the objects as it's falling down. Okay? So the idea of this is really that we now can have robot manipulators that can pick up objects and robustly, by using, in a sense, the real-time visual feedback to do this. Okay? Here's another example. With this kind of framework, we can also track, of course, human hands and human bodies. Again, this is tracking only, so we cannot initialize that position. Yeah. And one other area that we're looking at right now is actually this also motivated by some work. That Charlie Kemp works at Georgia Tech. So he's looking a lot at how robots can help people with physical impairments. Okay. Here he did some work with Henry Evans, who cannot move his body below the neck. Okay. So the question was, what are the kind of tasks that robots should be able to do to help his people, and they, for example, showed that the robot can help him shave himself, or even tasks like pulling up the blanket. And if you want to do these kind of tasks, it's not enough to track a person like through rigid bodies, but you need to actually track the full surface model of the person. So you need to have a much finer grained tracking system than the one I showed you. And here's something that we're looking at right now, which is kind of a combination between skeletal articulated tracking, where you can see here on the left a skeleton and a mesh, and this dynamic fusion approach where we are kind of deforming the model. So on the right you can see this work that Aaron is doing right now, where you can see on the left part is the raw input data, and on the right part is the object, the model that we are tracking of him, the surface model. So you can see that the surface mesh is actually deforming along with him. And this is not, again, this is not dynamic fusion, because we actually have underneath that model, we have a full skeleton and everything. Okay? So far I've been talking about this tracking work, and one of the main advantages was that we have like nice 3D shape models of things. Yeah. The problem with these, let's call model-based approaches, is that from an optimization perspective also, they just work in a kind of local basin of attraction, which means, for example, if you want to track the hands, then the tracker needs to be initialized with the hand position 1/30th of a second in the past. So the motion between frames is very small. The question now is, if the person comes into the frame, how do you initialize these models? And you cannot do this just through brute force search, because, let's say, the hand model is easily 27 degrees of freedom. So it's a 27th of search space. Okay. Another problem with these tracking techniques is also that once you lose track of the hand, there's no way to reinitialize it. Okay, so what we need now is an approach that can also detect the objects without having prior knowledge of where it is. Okay, and that's what I want to talk about now, how we can detect articulated objects. And that, of course, brings up some machine learning, because you just can't, again, do this, I think, through just a model-based search. So, and what motivated this work is also some work that came out of Jan LeCun's team, with Thompson did this, they had a SIGGRAPH paper, where what they did is, for hand tracking, is they collected data where they moved a human hand observed with 3 cameras at the same time. And then they had a technique similar to, let's say, DART, to track the hand with these 3 camera viewpoints. And if you can track the hand pose through this training data, then you can easily label points on the hand. Let's say I can point, let's say I want to train a neural network to detect the fingertip, then you can you can label that in the training data, and now you can train a neural network to detect that point. Okay, and here's something that my student Daniel did, which is very much based on this work, some extension. But the idea is very simple, where you say the approach is, you have this input depth image, the full depth image, and the first we do is we train a neural network to detect, to regress to a bounding box around the hand. Okay, so which is kind of where's the center of the hand and the width and height of the bounding box. Then we're going to train another neural network that takes, let's say, a zoom into this bounding box as input, and we train that neural network to regress to these different points on the hand that you can see on the lower right, okay, where they are in the depth image, and also how far away they are. Okay, now let me show you how this works on some real data. So what you see in the upper middle part is actually kind of a heat map output of the neural network where it thinks the bounding box is. And in the lower part on the right, you can see the different points on the hand that the network was trained to detect. So you can actually see that these estimates are very nice, consistent. There's no temporal reasoning going on, so every image is analyzed totally independent of the past. Okay, so you can nicely use this for initialization. In the middle on the lower part, you can see again these heat maps. Interestingly, again, we are not only regressing to the 2D pixel location of, let's say, the fingertip, but also to the distance. Now you might say that's trivial with a depth camera, right? Because the depth camera gives us the depth. But interestingly, what the network learns is, if from your viewpoint, if you're looking at my hand from here, and I ask you where the fingertip of my pinky is, it's not so trivial because you can't see it. Okay, so the neural network actually is able to have a pretty good prediction of where that finger is, even though it's not visible. So internally, the network actually learned kind of a structural model of the hand. Okay? So once you have something like this, you can also, of course, combine it with kind of a model-based like Dart approach and use it to initialize that. And then you can use that model also to do kind of the full model-based physics reasoning. Okay, and we're currently looking at more elegant ways of combining the model-based matching with the deep learning. Yeah. But again, I think this kind of initialization is something you could not have done easily without machine learning. Okay, I'm not going to claim nothing but deep learning could do this, but deep learning did it pretty well. Okay. Here's another example now. The work so far, the previous work depended on you have a big data set of the hand moving and you must have every point labeled by some approach. Okay? So here in this work, we wanted to see, can we learn kind of to detect points on a model in a fully self-supervised way, just using a technique like Kinectfusion or dynamic fusion. And the approach here is as follows. So this is Tanner. On the left, you can see a model that he built of himself using dynamic fusion, stuff that I showed you early on. And the nice thing is we can take any point on that model, like the blue point here, and for that point we can project it back into every camera image that was used to collect that data set. So what you see now in the middle here is the video that was used to build the 3D model, where we label at every frame we can label the pixel that was looking at that point on his forehead. Is that clear?
And it's blinking just so we see it better.
It's blinking so that you see it better, yes. But is the idea clear now? So again, we can now take that model, take any point, and say for any view onto that model, we can say which pixel looked at that. Now what we can do with this is we can use it to train a neural network using this kind of to give us data association. So on the right you see this is what's called a Siamese neural network, where the idea is we're going to present to the neural network two image patches. Yeah? And if the center of these two image patches or full images, if the center of them looks at the same point on the model from different viewpoints, then we want the network to generate on the output some kind of embedded representation for that patch that is very similar. So we want image patches that look at the same point on the model to be close in the embedded space, and points that are dissimilar, that don't look at the same position, they should be arbitrarily far apart. But up to a margin, they shouldn't be on top of each other. So what we're learning this way is in feature space or embedding space that has some kind of distance metric that relates to how similar points are on the 3D model of him. Okay? And we applied this to Kinectfusion and dynamic fusion. And if people want, I have some more numerical results, but we can, for example, learn features that are much more robust than SIFT features, for instance. Right? Or we can also learn features that don't only look at the visual appearance, but even that might have some similarity with respect to the semantics, which I'm going to show you one application of this right now. So imagine, now this is a video of Tanner, and again, we trained this similarity network on many videos that Tanner took of himself, and then used these videos to train the network, and now we have a video here, and we would like to match that 3D model into that image here. Yeah? So what we can do is we can first use our trained network to compute for every point on the model up here, the silver part, compute its embedded space representation. Let's say in this case we have a 3D embedded space. So the colors here represent kind of positions in this embedding space. And we can also go in the right image, and for every pixel in that right image, we can also compute its embedded space. Okay? And if this embedding was learned consistently across videos, then we can use a similarity function in this embedding space to do matching. Okay, so if you now look on the upper right panel, then we can use that model that we get from the left and match it into the scene on the right. And then we can even use the 3D shape in order to match it onto the depth camera. Okay, let me just show you some examples here. So what you'll see is on the left is the model, the sequence from which we built the model. And on the right, you will see how we match that into that new scene. So where the first part is just using it based on color and the embedding, and then we do some spatial refinement using kind of dynamic fusion. And you can see that the lighting conditions are very different between those different scenes. And the model was able to learn an embedding that is robust to these changes in lighting conditions.
Are you using RGB or RGBD?
For the initial matching for the embedding is only RGB, no depth. So it's pretty robust. And interestingly also, again, the model didn't only learn, for example, he was wearing different clothes in the different videos, right? So it's becoming robust to changes. So it detects your shoulder rather than, let's say, a blue patch or something like that. Okay? So now I want to move on to the final topic, which is very recent work on detecting and handling liquids, okay? Where the kind of motivation is, Julia Childs cooking, and in robotics we kind of try to stay away from these kind of things, right? In computer vision they call it stuff, right? But we humans are really good at reasoning about like liquids, right, or mixing things, so and things that are just not easily represented anymore, right? Like what is the correct 3D model for this? I don't know. Okay, and we have a very good intuitive understanding for when I'm pouring something, then the liquid goes from here into the bowl or something like that. So I just want to briefly show you one early line of work that we've done in the direction of pouring liquids. Yeah, and this is work that Connor Schenk has done. So initially we also looked at, can we actually in raw RGB videos, can we detect water? Actually detecting water is not trivial, right? Because it's just transparent, okay? And also the idea is, for example, if I want to pour you a half cup of coffee or something like that, it seems obvious, to me at least, that in order to do this, you need to visually see where the water goes so that you can know when you're done pouring enough, right? So people before that have done some work where it was about just emptying out something, emptying out a cup without spilling, but there was no visual feedback that they used in their controller. So what we want to do here is we want to be able that the robot can detect the water as it's pouring and then at some point decide, okay, that's enough. Yeah, because then it has some much more robust understanding of what's going on. So, and we want to do this without requiring any special hardware on the robot. So we've done some early work where we put actually the target container on a scale. And then you might say, pour 200 milliliters of water, and you just wait until your scale goes up. There are some issues that come up, like the scale has some delay, and then the transfer has some delay. So, but you can solve the problem that way, but it doesn't feel like being the right way that you always need your robot to have a scale with it. And also, some people mentioned what you might be able to do is use force feedback from the sensors in the arm to have kind of to measure the weight. But it turns out, for example, when we do this on the Baxter robot, it's way too noisy, so there's no way you can estimate actually the weight of the container in your hand. And also, we would like to be able, ultimately to be able to say, pour that bowl, make it half full. And half full, you don't even know how many milliliters that would be and things like that, okay? So I'll just briefly give you the high-level framework, and we're using deep learning to do this, okay? And the first network does the following, where the input is a color image, okay? And the output is, from the network is, for every pixel, it should tell us whether it sees water in that pixel or not. Okay, so this is a fully convolutional network. One interesting aspect here is that in order to do this, we're not only feeding in a single image, because from a single image, actually, tracking water is very difficult, and there's clearly something like optical flow involved. So we have a network here that's called an LSTM, which remembers information from previous frames and then uses that information to label the next frame better. Okay, and we did some experiments comparing different network architectures, and that is clearly the one that worked best. So again, the first network just takes as input the video stream and detects the pixels of water. The next network then takes the output of that, which is on the right kind of this heat map labeling. And from that, it tries to regress to how much water is in the cup. Okay, which is not quite as trivial because you have to kind of look at that area, and from that area you kind of then infer how much water is already in the cup or in the bowl. Okay, and caveat, a lot of this is clearly kind of overfitting to the data on which we trained the robot. Okay, so we had one table that you'll see in the videos, and we trained it on 3 different coffee mugs. You'll see that in one of the images. Okay, so but again, the goal is ultimately to go from the raw input to an estimate for how much water have I already poured. And once we have an estimate for that, we can put this very simply in a controller that just kind of rotates the hand. And if I don't have enough water in the cup, I'm going to rotate it further this way. And when I'm close to being done with the target amount, I'll just rotate it back. It's a very simple controller that is mostly based, of course, on the reasonably good perception that we hope to get. Okay, so now the question is, how do we actually train a neural network to detect water? The first approach was using simulation. So there are actually very good fluid simulations out there. You can see this here on the left. And to make it not too easy, we also overlaid videos on the background and rendered the video through the water so that the network couldn't totally overfit to a static background or something like that. So here you see, this is the input video to the neural network. These are the labels we get from the simulator, which is obvious. And on the right side, you can see the estimate of the CNN. So you can see that it's actually doing a pretty good job on detecting the water and not giving you all these false positives if there's motion in the background. Now, the more interesting task is, of course, so here you can see, and I must admit, this did not just work on real data. Because the water simulation is just, you can see the water comes out a bit clumpy or so, so there would have to be some more fine-tuning to just transfer that to the real data. But we wanted to, of course, get our robot to detect real data. And there we came up with a specific trick, and that is we attached to the depth and color camera of the robot, we attached a thermal camera. Now the cool thing is if you heat up the water, it's very easy to detect in the thermal camera. Okay, I'll show you one video here. So here you see the RGB, that's the thermal camera. And on the right side, you see kind of the pixel-wise labels that we get through thermal thresholding. We made the water very hot. Okay, so the cool thing is for this process now, we can collect a pretty good data set where we have pixel level labels in the RGB data where the water is. Okay, and now we can train another neural network to do this detection, and here you can see an example output where in the middle, color in the middle you have the thermal camera, and on the right you have the output of the neural network that's operating on the color data, not the thermal data. Okay, so it's not perfect, but you can see that actually it's giving us pretty good detections of the water. And you can also see in the video, it's not trivial to detect the water, right? Because there's all the, with the white tablecloth, or it's a towel in this case, right? So it's not a really simple task. Okay, so now with this network we can detect the water pixels, and then we train another network that goes from this detection to telling us how much water is already in the cup. Okay, and to do that, we also needed, of course, some training data. It turns out estimating volume just from the water you see is not easy, even for humans. It's very tricky. So what you see here is the 3 objects that we looked at, and in the upper, and lower level, there's always a 50 milliliter difference in amount, and it's really difficult to see on the water. Okay, it's just to show you that it's not a trivial task. To have 3 more minutes, is that okay? To finish this part? Okay. So because then I'm going to tell you, the question is now again, we need to get training data for a neural network for the volume that's in the cup. Okay? And how we did this is the following. So for these cups, we have the thermal data that detects the pixels with water. And then what we have is we can build a 3D model of the cup. We can match it into the scene, as you see on the right. And if you have a 3D model of the cup, and you know where the water is, and you know the viewpoint of the camera, then you can know which pixels that are looking inside the cup should see water or not, depending on how high the water is in there. Is that kind of clear? So using this reasoning on the right, so these 2 blue pixels should see water for that level. So using this kind of backwards in a Bayesian filtering approach, we can now use that to give us the model-based approach to tell us how much water is in the cup. And now again, we can use this to train a neural network to directly regress from the network detection of the previous one to the water amount. And then here's just, I'll give you 2 quick examples of how this now works. So what you'll see on the right is, of course, the robot pouring water. Here you see the robot is tasked to pour 200 milliliters of water into that bowl down there. Okay, and what you see in real time is the estimate of the neural network, how much volume there is, and this is the angle of rotation, and that is how we tell it to rotate, which direction. So here in this case we said, okay, pour 200 degrees, keeps on turning, 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 and then now the volume estimate goes up, and at some point says enough, and then it's rotating back. In this case, using a scale, we actually estimated the exact amount. It was 222. Okay? Here's another example. And interestingly, the neural network was not told which object it's pouring into. But we only had 3, so it's not like a major problem here. Let me show this. And again, the controller is very simple, right? The key trick is really to have the network that goes from the raw color data to these volume estimates. And here's just some experiments where what we show here on the X scale is the target amount of how much the water was supposed to pour. And on the Y scale, you see the amounts that it actually poured. So on the diagonal would be, of course, the correct amount. So it's like plus minus 38 milliliters, which is similar to, I think, what a human would kind of achieve on that task. It's not quite that easy. And the different colors indicate which target object we poured into. And interestingly also, so we did the amount in the cup from which the robot poured was also changed, so that the robot couldn't just learn, okay, to get 200, I'm going to rotate it for 5 seconds and then back. Right? It really had to use the closed loop control to do this. Just one very brief example, also now going to this because I talked about understanding activities in people. Here's some early work we did on activity tracking in cooking, where all we did was, so you have a recipe, and here you can see what the system is inferring about what's going on. And all we do is we detect these different objects. We can see which object the person is interacting with. And from that, using more or less just a hidden Markov model, we can then infer kind of what the person is doing. But I think in this direction, there's still a lot of work that has to be done. But I think this is something that we really need if we want to have these robots to interact with people in a more natural way. Okay, with that, I'm going to come to the discussion. Just in general, I think there were 3 main advances really that enabled a lot of this progress. On the one hand side, new sensing capabilities like depth cameras, and there's going to be new generations of these kind of cameras coming out. On the computing side, GPUs clearly had a huge impact. On the one hand side for, let's say, training neural networks, but also for all this tracking work that I showed you, GPUs are extremely useful for that. And also algorithmic advances, kind of understanding how we can take advantage of all this new hardware and computing devices. And I think we now have robots that are really able to detect, track, and manipulate objects far better than it was just like 5-6 years ago. So there's been a lot of progress, not only in my group, but really in the robotics community at large. And I think that building on these and moving forward, we'll have robots that are able to collaborate and interact with people in a much more natural way. And there are many applications domains for this kind of work. As I showed you, for example, one example would be healthcare, elder care, robots helping elderly people, or of course, small-scale manufacturing, science experimentation, like doing experiments in these wet lab domains, disaster response, and kind of general services in the home. So I think there's going to be many, many application domains for that. If you want, if I can have one slide briefly on some thoughts on deep learning, because I assume many of the students, so in our case, many of the students want to do deep learning these days, of course, right? And even like the grad students, when they come in, they say, yeah, I want to do deep learning. And I think on the one hand side, so my experience has been that on the really plus side, it's an extremely flexible framework, right? That can do these kind of tasks, especially based on perception, that beforehand we at least didn't know how to do. For example, the water pouring stuff, like how to detect water and things like that. So it's really powerful for learning these from raw data. I think in many tasks, also in robotics, these kind of techniques will dominate a lot of the stuff that we're doing. So we'll see more and more of these approaches. So I would suggest, at least if you're working in this domain, not to totally ignore the advances coming out of that community. In robotics, one question is often, where do you get the label training data for if you want to do recognition tasks? In robotics, the advantage, if you look at temporal reinforcement learning tasks, then the future data often gives you the training signal that you use for your current data. So this is why I think these deep learning techniques will be very valuable and applicable, especially also in robotics. There are many open questions, like where do we get all the training data from? I think simulation might play an important role, but there's the big question of how to go from simulation to real data. A big question from my perspective is how do we really, in a nice way, combine this model-based reasoning with deep learning techniques? What is the right way of doing this? How do we get uncertainty out of the deep learning approaches? And how do we generalize across tasks? So I think many of the techniques or the results we are seeing these days kind of really overfitting to specific settings. And I think a big risk is really, it feels sometimes like the students are kind of degraded to network engineers, which means you try to solve a certain problem and you throw your deep neural network at it and it doesn't work, right? And then you spend the next 5 months on trying to come up with the right network structure, or you're searching through this huge space of network structures, hyperparameters. How do you present your training data? What is the right kind of a training regime that you're using? So there are many, many open questions, and since we don't really have systematic ways of approaching them, it's kind of like many of the students get there and they have to do this kind of search through the space of possible network structures. And that takes a lot of time and is sometimes frustrating. And of course, there's this risk that if you're a big company out there that is interested in deep learning kind of stuff, and they have all the GPUs, then it's really difficult to compete with them. So we got to be careful of working on stuff that they might not directly compete with. That's also, even it seems sometimes like the research output of students is kind of linearly correlated with the number of GPUs they have access to. But as general, I think it's a really, really valuable toolbox that we should take advantage of, and it can have a really big impact on what we can do. And with that, I'd like to thank you and thank also the students that were involved in this line of work that I presented here. Thanks a lot.
So we can open up the room to questions.
Yeah.
When you were tracking feature points on a hand, this goes back to the middle of the talk.
Yeah.
You said that the neural networks were actually able to track it even though they might be included in the current scene. And I didn't quite understand how that's going to happen.
That's a good, because in the training data, so for the training, we used 3 cameras, or they to generate their training data, which wasn't us, they used 3 cameras. And with 3 cameras, you can actually track it. And then they trained the network to track the hand from a single viewpoint. So it might be occluded from this viewpoint, but that camera was able to give you so the data had the supervisory signal of where the pinky was. So you need to give it the thing, but then it's pretty cool that they do that so well. Yeah.
How much did you use both simulation data and the heat map
Oh,
data?
that-
The final.
That's a great question. So for the final data, we actually right now, we only used the RGB, only the real data in the end to train. Well,
For training,
let's
you
see.
can't use the heat camera.
Yes. No, so for training, we use the thermal camera, gives us the labels on the color camera.
Yeah.
And then we train a network that goes from color data only to detect the water.
Right.
But simulation data was not used for that.
In that part, not, but in the simulation data, we also did some other reasoning. The advantage of the simulation data is that it can tell you where water is that isn't even visible. So which means if there's a coffee mug and I'm pouring water in here, the thermal camera only sees the water going here, but not the water in the... So we also tried to train a neural network that detected water, or that reasons about water that is not visible. And the simulator gives you that kind of information.
And,
Yeah?
and how much data did you use?
Oh, it's actually on the pouring for this. I don't think it was like 160 pouring sequences. No, but again, the caveat is, at this point, I expect this to work on that table,
Oh, and like nowhere else.
right?
Yeah.
So it's not quite as bad like nowhere else. So we're looking also, we're generalizing across objects and stuff like that right now. But I think if you want to have a really robust system, then you need to collect a much larger data. So what we're thinking about is having, so we are aligning the thermal camera with the color camera and have it kind of for a person. And then collect data where you're just kind of playing with water and label it. And then I think it's mostly a question at this point of getting enough training data, right? It's not a fundamental limitation, I hope at least. And I think it would be cool if we would get the robot to be just very robust at detecting or reasoning about this water, right? Because then training controllers or other things on top of that should be reasonably, not easy, but doable. Yeah.
So before you're showing a demo of the robot building a model by rotating an object, but if the object is a container with like a bag of marbles or something that's supposed to go on the floor, is there a way
Yes.
of, like preventing it from making that bad of a mistake?
Oh, so you mean if it picks up a cup with water in it?
Yeah.
Oof. At that time, we didn't even think about this kind of problem. But you're right, that we couldn't handle that right. I can imagine you could, of course, now you could maybe go back and reason about even what could be a container, right? Or what could contain water, and then you could maybe take that into account. So we're also thinking about, so with the water stuff, one real limitation is I wouldn't say that the approach has any, let's say, real idea about water, right? It's only labeling pixels in an image, more or less. So where we want to go is a much more capable reasoning systems that can reason about water, like the fact that if I'm pouring from here and then later there's water in this bowl, that this is the same water that came from here and these kind of things. So we're now looking at how we can connect that to real fluid simulation so that we can track the state of the fluid simulation using the water detected by the neural network. And then hopefully we have much more capable reasoning on top of that too.
Did the model know how big the cups were, or did it also have to learn that?
That was learned, so for the volume estimation, I guess, you assume. So volume estimation, to get the training data, the ground truth volume, that model has a shape model of the object to get the volume, but the neural network wasn't told about that. It had to learn that. But again, well, I could imagine if you train this on enough objects, right, and with enough background, then it should actually become reasonably robust to even totally new objects to doing that. Yeah.
I'd like to ask your opinion on like approaches that use deep learning from end to end that like outputs joint torques correctly versus like approaches that use that generates like intermediate labels and then use that afterwards. Like how do you? What's your thought on that?
Yeah. I think ultimately it's going to be really kind of the right combination between different frameworks or different model-based approaches or things like that and the deep learning. So, for example, in the water pouring case, if you wanted to learn a neural network, just saying, here is the video, and you just regress it immediately to the volume. I think Connor tried that. That would not have worked, because the connection between the volume that's in the cup or in the bowl and the image is just so indirect that you don't even get the good gradients when you're feeding that back, right? So I think this approach here, for example, where we first train a network to detect the water and then the other one on top of that, seems like, at least for pre-training, a good way. You could now take these two networks and stack them together and just retrain or fine-tune it jointly, right? But I think at least kind of for initial training purposes, having this additional signal really helps. But in general, I think sometimes the just end-to-end training is the question of how well it will translate to new tasks, right? And there might be certain components that you might want to train a network on, and those components can translate very well to new tasks. So that's a question on how you train them. But we'll see how far we can get with that stuff. Yeah.
When predicting of objects containing a person, right? Prediction of person, like, is it variant on the facial features or such, or the age? Is it like, if you have a model of a person like 5 years, like from now, would they be able to successfully match the person? And what another question I had was like regarding twins, like if you have two views in the same image
Oh.
model, how well does it do to map it to two different identities, or how well does it match?
Yeah, that's a great question. Right now, on that data we did, so it's actually, Tanner used only data that he collected of himself. So we didn't even test it so much on the discrimination among people. I think in that case, you would maybe have to label data where you say this is a different person from that, so you want to learn an embedding where these are set apart. Right? So right now what's interesting in this data, so he collected 60 videos of himself, and this approach of using dynamic fusion to label the data association only works within each video. It doesn't tell you cross-video associations. But interestingly, it did learn an embedding that is consistent across videos. Right? But you're right, the big question comes up, like if you want to discriminate among people, or how robust are you really for a single person even. And I think that's also, we just need to collect more data to look at that.
It's likely
Good
that
question.
it would work even if the target was a different person, isn't it? You could just map it over there.
It should do reason. I think especially if you would learn the features on the depth, right? So right now these features were only learned on color. You can easily incorporate depth as well, and I think that would be a bit more robust with respect to matching to new people or so.
Okay, I think we should stop now, unfortunately, because we are running out of time. We're over time. If you have
Sorry.
any more questions, you can come over here. But first, I'd like to thank Peter again for being here.
Thank you.